Hello ladies and gentlemen, my name is Marwan. I am from University Grenoble Alps, and together with Roman Brusier and Ludovic Metivier from the same university, as well as Thomas Bolen and Yudipan from Karlsruhe Institute of Technology, we would like to share our research, which is sponsored by the SEG Consortium regarding the component analysis of 3D elastic 9-component full waveform inversion, especially for the Ettlingen line case study. I would like to begin our presentation with the full waveform inversion itself. FWI is based on an iterative data fitting procedure which theoretically can use all of the recorded data. Therefore, it is really efficient and there is no specific data extraction required to perform directly the FWI. It is expected that this FWI can yield a high resolution seismic imaging up to the half of the inverted frequency, at least in theory. This FWI works really well for seismic exploration scale, especially when we use the acoustic approximation. As you can see on the figure on the right, at the top is the initial model which was obtained from the travel time tomography, whereas at the figure at the bottom is the result from the FWI. You can see the increase of the resolution and the clarity due to the usage of FWI. The popularity of the FWI does propagate to the shallow seismic community as well, because there are gains of interest of FWI application for this particular scale. For example, last year, a group from Princeton published a research about the underground tunnel detection, where you can see here at the top is the vertical section, whereas at the bottom is the horizontal section at 10 meters depth. You can see now the scale is not in terms of kilometer, but only 150 meter and 30 meters depth. So it's really small. And you can see the target is given by the white box and here. And thanks to the FWI, this is the FWI result. You can see the shape and the structure of the underground tunnel. But before we go into a further detail, I would like to share with you what is the current challenges of the FWI in shallow seismic scale. The first is that the wave usually have strong presence of the elastic effect, and this elastic effect is usually manifested in the form of the surface wave. As you can see on the figure on the right, the huge amplitude here which dominates the data is the surface wave. So that is one problem, and we can no longer use the acoustic approximation and we need to move towards the elastic approximation. The second thing is that we have a relatively high attenuation effect, usually in near surface or in shallow seismic scale, which make it difficult to propagate in high frequency. Because when we go towards a higher and higher frequency, we have less and less information about the medium due to this high attenuation effect. The next challenge is that we generally have low number of seismic channels, and also there are just a few, or maybe almost it's quite rare to have the application of multi-component source and multi-component receiver, especially multi-component source. Therefore, we have already performed a field experiment and we have already performed 3D elastic FWI, and I would like to give you the brief introduction about both of those. Generally, we would like to perform FWI on shallow seismic scale, only 32 by 28 meters, and we would like to perform 3D elastic FWI, which in the end will give us both VP and VS, so it's multi-parameter inversion. The target is the Ettlingen line, and you can see the Ettlingen line on the figure A here. This Ettlingen line, which is a war trench, so it's a historical war trench which was built on 1707, so around 300 years ago by the German troops during the War of the Spanish Succession. You can see the existing Ettlingen line given by the red line here and here, and on the field the Ettlingen line looks like a figure D, but at some part of the region, especially in our field, this Ettlingen line has been leveled to the ground due to the development of the airfield probably in this area, and we would like to perform 3D dense seismic acquisition in this specific white box in order to reconstruct the geometry of the Ettlingen line. We use a multi-component source and multi-component receiver, and in terms of the receiver we use 3-component geophone, and we use a specific multi-component source, a so-called the Galperin source, and you can see on the figure C. And this Galperin source has a specific direction U and V and W, which is not parallel to the Cartesian coordinate axis. In terms of the acquisition geometry, we have in total almost 900 receiver, which can be seen on the figure on the right with the inverted triangle. And you can see there are 6 different color of the receiver. This is due to the fact that we have limited equipment. Therefore, we need to perform our acquisition part by part. In order to perform the FWI, we have already performed an additional data correction through matching filter, which has been published on my previous abstract. In total, we have 36 source locations, which will be used during this FWI, given by the black circle. The idea is to perform a multi-parameter FWI following this particular strategy. The first is that we follow a multi-scale FWI. You can see on the flowchart there, the multi-scale FWI is represented by this loop. And it is generally an FWI starting from lower frequency band, in this case is 3 to 15 Hz, to a higher and broader frequency band with the increment frequency of 10 Hz. And inside of each scale, we have two spared FWI. The first is that we have a parameter binding FWI. You can see the parameter binding FWI here. And the idea of this parameter binding FWI is a hard constraint VP with respect to VS. The second FWI is a nonlinear model constraint. And in this nonlinear model constraint, we have update for both VP and VS. So it's a true multi-parameter inversion where the update of VP and VS can be done independently. But we impose an additional constraint of VP over VS ratio, so it won't go beyond a physical reasonable limit. Finally, by following this strategy, we can start from the homogeneous initial model to a relatively nice final shear wave velocity model in which we can reconstruct the shape of the Etlingen line here. This is the Etlingen line, as well as the other low velocity anomaly. So this is the other trench-like structure, which up until now we do not know what is the historical significance of this trench. Now it's nice that we can already perform the FWI using all the 9 components, and we can obtain a relatively nice result, but there is still a question of the necessity of this 9 component data. Do we really need this 9 component data to perform FWI, especially in this particular case? And if yes, what will be the benefit? So we would like to answer this question throughout this abstract. So in order to do that, we have already prepared an experiment setup and also an assessment strategy in order to measure the quality of our inversion. We have 2 experiments in this abstract. The first is we have field data experiment. As we know before, I have already explained you what is the acquisition geometry, what is the source type, and in which we have the Galperin source, and so on and so on. The second experiment is the synthetic experiment, in which we would like to kind of generalize our problem towards more classical usage of Cartesian direction source. In this case, the source direction is a vertical and horizontal source. For each experiment, so for the field experiment and for the synthetic experiment, we have in total 16 different FWI. We have 9 single component FWI, we have 3 component source FWI, we have 3 component receiver FWI, and 1 9 component FWI. And in order to assess the quality of our inversion, we determine 2 quantitative ways to measure the quality. The first is that we use the data misfit. In this case, we use a classical L2 norm for each component. And the second is model misfit, in which we use the normalized least square. You can see that here on the equation 1 is the model the equation for the model misfit, in which for each value is normalized by the reference model. And this reference model is ideally is the true model, and it is easy for the synthetic data because we exactly knew what is the true model. But for the field data, this is quite tricky because we do not know what is the true model. Therefore, we take into account our previous experiment, in which we invert our data up until 65 Hz using several different initial model, and we use those previous model as our reference model. So that is the closest we can get from the true model. Now we can start to discuss about the result and the discussion. You can see here, this is the model reconstructed using all of those 16 FWI. There are 3 different sections here. The figure A here, the first section is the horizontal section at 1.5 meters depth. The B section here is a vertical section which is perpendicular to the Etlingen line, so it's around this direction. And figure C is the reconstructed model, the vertical section of the shear wave reconstructed model, which is parallel to the Etlingen line, so this direction. Now we can begin to see on those figures. Given by the red box is the reconstructed model from the one component FWI given by the blue box is the reconstructed model from the three component receiver FWI, and this one, the green one, is the from the three component source FWI, and finally the black one is from the 9 component FWI. It's a good thing to see relatively consistent, at least at 1.5 meters depth, where we see that all of those 16 FWI is quite similar one to another. So at least at the shallower depth, even using single component FWI, it is sufficient and it's quite comparable to even the 9 component FWI. When we go towards the vertical section here on the right, on the figure B and C, we can directly pay our attention to the vertical component here, where the reconstruction at depth is not as good as if we use the horizontal component, for example here X, Y, and 3 component receiver. So even by visual inspection, we can already see that the horizontal component is crucial towards the FWI for shallow seismic scale. When we go towards a further analysis of model misfit, we can see a good agreement with our previous statement, in which when we look at the highest three of model misfit, we can see that those three are related to the UZ, VZ, and WZ component. Therefore, the usage of horizontal component in this case is really beneficial towards our model reconstruction, especially when our target is quite deep. When we look at the data misfit, though, it's a bit complicated because there are just too many information, but we decide to represent the data misfit by the color. In this case, the red color means the higher misfit and the blue color means the lower misfit. I will take one example of the FWI using UZ component, so this particular FWI. By using UZ component, you can see that the component which is taken into account for the FWI is given by the bold border here, and you can see all the 9 different components. All of this represent the data misfit, the absolute data misfit from each component. You can see that amongst all of those 16 FWI, the pattern of the color is relatively similar. We can see strong absolute data misfit in VZ and relatively low data misfit on UY and WY, and it is quite consistent in all of the 16 FWI. And this explains why the reconstructed model is not that far one from another, and to find which component is better compared to the other component is trickier, because we have different contribution of the wave coming from one component and another component. We cannot directly compare one component and another component using this kind of plot. Therefore, we design another plot in order to have an easier understanding of what is really happening in our data misfit. The idea is to take each sample of the component from each FWI. So in this case, I took UZ component, so all those 16, and we just put it like that, and we just sort it to find out which one has the lowest misfit and which one has the highest misfit if we compare only with the same component amongst all the 16 FWI. And turns out for this UZ component, we obtain the misfit grade. We call it misfit grade on the right here, and we can see directly that this one with the 9 component has the blue color, and this blue color represents the higher grade. It means that it has the better data misfit, so it has less data misfit. Whereas here you can see a consistent reddish misfit grade, so the worse data misfit compared to the other data misfit. And you can see this consistency with the previous model misfit and also the visual inspection, where we have the vertical component, we have relatively low quality of inversion, especially at depth. And when we apply this kind of misfit grade technique throughout all the components, you can see here on the figure on the right, now the image is not as simple as the previous one, but we can see several interesting patterns or result. The first is that using all the 9 components, it produces almost the base misfit grade for almost all the components except single component here, but generally it produces the best data misfit, the best misfit grade in this case. The second thing is that using 3 component data, for example here, And here, disregarding this part of the three component data, we generally can see that the misfit grade is goes toward a higher grade compared to the one if we use the single component data. This part is really important as well, because even though we use three component data, the result might not be satisfactory if we only take into account the vertical receiver component. So the influence of the horizontal component in our model reconstruction is really crucial. When we move towards the synthetic experiment, here I will directly present you the model misfit, because the reconstructed model is quite similar to the previous one. The model misfit here, it is relatively consistent that when we have the influence of the Z component here, Z, we have also a relatively high model misfit. So this is confirmed because for the synthetic experiment, it's quite consistent as well. So again and again, the horizontal component is proven to be quite crucial in our shallow seismic scale. Although it is important as well when we look at this special case YY here, the model misfit is not as high as the other horizontal component, but it is still comparable. And this is mainly due to the fact that we only have single component data, and it turns out that if we have single component data, we have less constraint and less illumination inside our medium. Therefore, our inversion might stuck in the local minima as well. And this is one of the emphasis why we need to move towards multi-component data if it's possible. When we look at the data misfit, we can see that the data misfit using this simple setup is relatively simple as well. There are only three dominant components in this case: ZZ, XX, and YY. And in practice, if we decide to use only classical direction source and receiver, it is maybe important to mainly consider those three components and try to focus on those components, so our acquisition can be more efficient and effective. That will work for especially for the relatively simple model, just like in our case. The next thing is that we still see the consistency, another consistency here, where we see the vertical source component and vertical receiver component. We can see that the absolute data misfit, directly from the absolute data misfit, the quality is not as good as if we use the horizontal component. And those experiment and our observation regarding the horizontal component reminds me on our previous research regarding the sensitivity kernel analysis of the surface wave, where we try to plot the sensitivity kernel of only the surface wave here, and to see on the VS gradient, we can see that here when we use the vertical component, we have really less penetration depth. Even here when we use the vertical component, this is the receiver component, it's still the penetration depth is still quite shallow. But when we use this horizontal component, we can see that we have the advantage of having this YY component as the loft wave, which give us a deeper penetration depth. So the physical meaning of why we need to emphasize on the horizontal component is because of the an additional information of this loft wave and also the radial component of the Rayleigh wave. And in conclusion, the FWA has shown to improve the subsurface model even using one component data. The second is that the reconstructed model are quite consistent, reflecting a working workflow. The third is that the horizontal component provide crucial contribution in terms of the model reconstruction, and this is due to the fact that we have an additional information from the loft wave as well as the radial component of the Rayleigh wave. The multi-component data acquisition is always recommended to increase the illumination and data redundancy. Although, if we have a limited number of equipment and the component selection, FWI with a single component still can produce a sufficient accuracy, but we need to focus mainly on the horizontal component in order to get a better model reconstruction both in spatial and in depth. In the future, we would like to analyze the variation of the number of the source and the receiver, which coupled with the impact of multi-component data. Finally, I would like to give my thanks to all the collaboration between several university and research center, as well as the SEG Consortium and all of the sponsor and the DFG German project, as well as the Siemens Ines Idris and the GCC Computing Center. Thank you very much for your attention.